In this mini lecture, we are going to explore the quantum behavior of electrons. As you recall, previously we explored the quantum behavior of photons and saw some rather surprising results. We found that depending on the type of experiment you perform, you get a different answer as to whether or not light is a particle or a wave. So we used this double slit experiment and we saw an interference pattern showing up, and we used that to conclude that light is in fact a wave. But then the photoelectric effect indicated that light was in fact a particle, which led us to an inescapable conclusion that light is in fact both a wave and a particle. And the type of answer that you get to this question depends on the type of question that you pose. In other words, if you ask a wave-like question, for example, looking for interference, you get a wave-like answer, namely the interference pattern. If you ask a particle-like question, as we do in this photoelectric effect experiment, we get a particle-like answer. In this video now, we are going to ask these same sorts of questions, but now focus on electrons. So in doing this, we're going to actually follow the same sort of experimental path that we did with photons initially, and we're going to actually perform a double slit experiment, but this time we're going to use electrons as the particles being fired at that double slit. And then we're going to use the results of this double slit experiment to motivate the so-called de Broglie relationship. Okay, so on to the double slit experiment with electrons. Let's take a moment to look at our experimental setup. So what we're going to do is we're going to use an electron source. We'll just call this some generic electron gun, whose job is to fire little electrons at a barrier that has one or more slits in it. Then on the far side, we are going to have a detector that will essentially count both the number and location of individual electron impacts. So it'll show up as a little blip of electron. It's here, 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 here. So if we cover up one of the slits here, so we only have one open slit, we'll call it S1, and we start shooting electrons, the first question we want to ask is, okay, well, what sort of pattern builds up at that detector? So if electrons are behaving as particles, what sort of pattern would we expect to see over here? This would be a good time to go ahead and pause that video and try and draw out a little diagram that would illustrate the pattern that would be built up by the individual electron impacts at the detector if only one slit is open. Okay, well, if electrons are acting as particles, they're either going to go through and impact the detector or not. They're going to bounce back and do something else. And so depending on the trajectory of that electron, they can only travel in a straight path. So even if they were coming in a little bit of an angle, you'd still sort of be cut off here. And so as a result, what you would see over time is a buildup of individual electron impacts where the peak, highest number of impacts are lined up right collinear with that opening of that first slit. And of course, if we opened up the second detector, we would see a similar sort of pattern, although this time the maximum number of electron impacts that are recorded would be lined up with the opening of that second slit. So not terribly surprising. These experimental results essentially verified what we already thought we knew, namely that these little electrons are behaving like particles. Okay, so now let's make things a little bit more interesting. Let's go ahead and open up both of the slits to form our double slit. And then take our electron gun and shoot a bunch of little electrons at this double slit, and then ask the question, well, what sort of pattern would we expect to see at the detector? So if we go back to the previous two slides and we assume that these electrons are behaving as particles, then we can consider electrons that are coming through this top slit. We'll go ahead and color the top slit if they're going through S1 green. Right? We saw a pattern that was built up that looks something like this, where the peak of that distribution of electrons is right lined up with that opening in slit 1. Then let's go ahead and do the same thing for the second slit, and of course we're going to see the similar looking distribution, although this time lined up so that the maximum or highest number of individual electron peaks is lined up directly with S2. Okay, so if those are the two patterns we would expect for either the electron going through slit 1 or slit 2, and the electrons are behaving like a particle and go through either slit 1 or slit 2, then the pattern we would expect to see at the detector would be a simple sum of both of these green and blue distributions. However, if we actually do this experiment, you will probably not be surprised to learn that the impact pattern that we observe at the detector is different. All right, so go ahead and pause the video for a second and try and come up with a prediction of the kind of pattern that we would see at this detector. So it turns out that we see an interference pattern. In other words, we see regions where there's a lot of electrons impacting that screen, and there's regions where there are absolutely no electrons impacting those screen. This was analogous to the alternating light and dark patterns we saw in the double slit experiment when we use photons, or a beam of light. Okay, so this is interesting, but someone might say that, well, perhaps these electrons, we've got this whole bunch of electrons which are still particles, but they're traveling somehow in waves, and these electron waves are then interfering with one another, similar to how a bunch of water molecules come together and form ocean waves that could interfere with one another. So to get a little bit better feel for what's going on, let's change this up to essentially account for that possible explanation by just firing a single electron, one electron at a time, let it go through the double slit, and note where it impacts the detector, and then after we record that impact, then we'll fire our next electron, and then figure out what sort of pattern ends up forming. So if we shoot our first electron, we'll represent it by a little dot. Right? Our first little electron goes through and it shows up at the detector. No big surprise. Right? Then we shoot another electron, shows up at the detector. And we do it again, and do it again. And if we keep doing this a bunch of times, we end up seeing a pattern that looks like this. There are regions where there are no electron impacts, and then regions where there's quite a few electron impacts. In other words, we come up with an interference pattern. Now remember, we're firing only a single electron at a time. So this single electron is somehow interfering with itself in order to give rise to this interference pattern. So how could it be possible that electrons are interfering with themselves? Well, it's simply not possible if that electron is a particle. The only way that we can make sense of the double slit experiment using electrons is by drawing the conclusion that electrons are in fact waves. Now let's keep going with this, and actually things will get even stranger. So let's suppose that we keep with the experiment of firing a single electron at a time at this double slit. But now we're going to change things up a little bit. We're going to fire a single electron, but now we're going to use a second detector that doesn't stop the electron, but basically makes a little note of, did the electron pass through this slit or not? And because there's only two slits, if we have knowledge that the electron went through the first slit, then we know that it didn't go through the second slit down here. And so similarly, if it didn't go through the first slit up here, S1, then we must conclude that it did go through the second slit. But keep in mind, we are not altering the path. We're going to let the electron just keep going right on through. We're just going to watch it go by. So this would be like me sitting in my office and watching students go walk through the hall. I would know that saw the student walk through the hall, but I didn't stop them. I allowed them to just keep passing through. Okay, so now we're going to ask the pattern once again. What sort of pattern would you expect to see if we place this detector at S1, at that first slit? Remember, both slits are open, so this electron can pass through both slits. And we just saw that if the electron can pass through both slits, we end up with this interference pattern. Okay? So the only thing we've changed here is the presence of this detector. So go ahead and pause the video for a second and make a prediction as to what kind of pattern you expect to see at the detector. Okay, so it turns out that what you actually find is a pattern that looks like this, which is a sum of the electron going through the first slit up there and the second slit down here. And this guy should be red. Okay, so this doesn't make much sense, right? We allowed the electron to keep going through both slits. We didn't do anything to stop its path. Yet somehow, the very fact of observing this electron, just knowing that the electron went through either the top slit or the bottom slit, forced the electron to behave like a particle. So what we've essentially done by asking the question, which slit did you go through, Mr. Electron? We are forcing that electron to give us a particle answer because it's a particle question. And so then, not surprisingly, if we move that detector down to the second slit, you again get that same sort of particle-like behavior and a resulting pattern at the detector that's just the sum total of the electrons passing through both the top slit and that bottom slit. So this is now another strange aspect of quantum mechanics. It turns out that the very act of observing a system causes that system to fundamentally change. In other words, we're forcing that electron to choose either the top slit or the bottom slit by placing the detector at either one. And if we remove that detector, then we're no longer forcing a choice, and so as a result, this electron behaves as a wave, and that wave interferes with itself and causes an interference pattern that we observe initially. Okay, so this was a lot of strange stuff, so let's take a minute to summarize what we've observed. So we saw that firing single electrons at a time results in an interference pattern. And so our conclusion from this is that electrons must have wave-like properties. We also saw that placing a detector at one of the slits destroys the interference pattern. And so we found that the act of observing a system, right, by asking a particle question, forces a particle answer. And so this is strange. It means that just like photons behave as both particles and waves, electrons turn out to behave as both particles and waves. And in fact, all fundamental particles behave as both particles and waves. Well, if particles behave like waves, then they should have other wave-like properties, for example, wavelength. So that brings us to our final section here with the so-called de Broglie relation. The de Broglie relation essentially gives us a way to determine the wavelength for any object. And it's a very simple relationship. Like a lot of the equations we're seeing in this section, the wavelength of any body, lambda here, is given to us using our good friend Planck's constant divided by mass times the velocity. So another way we could write this is Planck's constant divided by p, the momentum. So to see this in action, we can calculate the de Broglie wavelength for a 0.145 kilogram baseball that's traveling pretty darn quick, almost 1,500 meters per second. So to calculate this, we just plug directly into our equation 1 above, using the Planck's constant. Make sure that we are recording at least 4 sig figs there, because our problem's coming in with 3, and we arrive at a answer of 3.14 times 10 to the minus 36 meters. So this little example actually illustrates why it is that if we don't see any of this wave-like behavior, despite the fact that all the little particles that make up everything around us do in fact behave like waves and particles. The reason is because the waves the wavelength for these objects, any object we see at a macroscopic level, its wavelength is going to be so teeny tiny that there's no way that we could ever observe something that small. It's beyond the realm of something that modern day, technology would allow us to probe. So in our next example here, we're going to look at an instrument that we use to probe matter at one of the smallest scales that we can. So one of the best experimental techniques we can to look at the teeny tiniest, best resolution we can pull out is the so-called electron microscope. So the electron microscope uses highly accelerated electron beams and shoots them at a sample, looks at how they bounce off, and builds up a picture of what that object looks like. So if you look at the electrons that are being accelerated in this electron microscope, it turns out that they are accelerated to a momentum on the order of 4.3778 times 10 to the minus 23rd kilograms meters per second. And so if we want to figure out the wavelength of these electrons that have shooting through this electron microscope, we can go back to our de Broglie relation and use the fact that mv equals p and come up with this expression. We can then plug in the values of the known and unknown parameters and arrive at our final result. Now I want you to take a minute and look at this result. Remember that the units of Planck's constant are joule seconds. So I want you to go ahead and look at the definition of joules and seconds, kilograms, meters, and seconds, and convince yourself that these units cancel out to give you units of meters at the end of the day. Second, I want you to take a closer look at the number of significant figures involved in this calculation. So the value that we were given, 4.3778, right, has a total of 5 significant figures. The value for Planck's constant that we've been using for most of our calculations so far, we were truncating at only 4 significant figures, right? So this is a problem. What we've effectively done in this case was limit the accuracy or precision of our final result to only 4 significant figures, which is not something that we should do. A lot of work went into taking this measurement. This one, right, we just copied off of a table of constants. So in reality, what we really should have done is included more digits, significant digits, in that Planck's constant. So to sum things up, right, we've found that electrons, and in fact all matter, behaves like both wave and particle, and the type of behavior you see depends on the type of question that you ask. You ask a particle question, you get a particle answer. You ask a wave question, you get a wave answer. This holds for photons now and all of these little subatomic particles that make up everything around us. Second, we saw through the de Broglie relation that we can calculate the wavelength for any particle, any collection of matter that has a mass and velocity and momentum by simply using Planck's constant in this relationship.